Maximum length of overhang, often abbreviated as MLO, is a measurement that defines the maximum permissible distance an overhanging structural component can extend beyond its supporting structure. This measurement is vital for ensuring the structural integrity and overall safety of various engineering designs and installations. The concept of MLO applies across different fields, from civil engineering and construction to electrical distribution systems. In the context of structural engineering, MLO dictates how far a balcony, canopy, or any other overhanging element can protrude without compromising its stability. Exceeding the MLO can lead to excessive stress on the supporting structure, potentially resulting in deflection, cracking, or even collapse. Factors influencing the MLO include the material properties of the overhang, the load it is designed to bear, and the design of the supporting structure. Engineers use structural analysis techniques such as finite element analysis to determine the MLO for a specific design. This analysis considers various load combinations, including dead loads, live loads, wind loads, and seismic loads, to ensure the overhang can safely withstand all anticipated forces. The material properties of the overhang, such as its tensile strength, compressive strength, and modulus of elasticity, also play a critical role in determining the MLO. A material with higher strength and stiffness will generally allow for a greater MLO. The design of the supporting structure is equally important. The supporting structure must be able to transfer the loads from the overhang to the ground without excessive deformation or stress. The design of the supporting structure may involve the use of beams, columns, walls, or other structural elements. In electrical distribution systems, MLO refers to the maximum allowable distance an overhead transmission or distribution line can extend beyond a support structure such as a pole or tower, without requiring additional support. This measurement is crucial for maintaining the reliability and safety of the electrical grid. Exceeding the MLO in electrical systems can lead to several problems. Firstly, it can increase the sag of the conductor, which is the vertical distance between the highest and lowest points of the conductor span. Excessive sag can reduce the clearance between the conductor and the ground or other objects, posing a safety hazard. Secondly, it can increase the tension in the conductor, which can lead to conductor breakage or damage to the support structures. Thirdly, it can increase the electrical stress on the insulators, which can lead to insulator failure and power outages. Several factors influence the MLO for overhead electrical lines. These factors include the conductor size and weight, the tension in the conductor, the weather conditions, and the terrain. Larger conductors generally require shorter MLO due to their increased weight. Higher conductor tension also requires shorter MLO to limit sag and stress. Weather conditions, such as wind and ice, can significantly increase the load on the conductor, requiring shorter MLO. The terrain also plays a role, as uneven terrain can increase the risk of ground clearance issues. To ensure compliance with MLO requirements in electrical systems, engineers use specialized software and tools to model the behavior of overhead lines under various loading conditions. These tools allow them to optimize the design of the line and the placement of support structures to minimize the risk of exceeding the MLO. Regulations and standards, such as those established by the National Electrical Safety Code (NESC), provide guidelines for determining the MLO for overhead electrical lines. These guidelines take into account the factors mentioned above and provide specific requirements for different types of conductors and support structures. Adhering to these regulations and standards is crucial for ensuring the safety and reliability of electrical distribution systems. The consequences of exceeding the MLO can be significant. In structural engineering, exceeding the MLO can lead to structural failure, resulting in property damage, injuries, or even fatalities. In electrical systems, exceeding the MLO can lead to power outages, equipment damage, and safety hazards. Therefore, it is essential to carefully consider the MLO during the design and installation of any structure or electrical system. To further elaborate on the importance of MLO, let's consider some specific examples. Firstly, consider a balcony extending from a building. The MLO for the balcony will depend on the materials used for the balcony, the load it is designed to carry, and the design of the supporting structure. If the MLO is exceeded, the balcony could deflect excessively, crack, or even collapse. Secondly, consider a canopy over a doorway. The MLO for the canopy will depend on the materials used for the canopy, the wind load it is designed to withstand, and the design of the supporting columns. If the MLO is exceeded, the canopy could be damaged by strong winds or even collapse. Thirdly, consider an overhead transmission line spanning between two towers. The MLO for the transmission line will depend on the conductor size and weight, the tension in the conductor, the weather conditions, and the terrain. If the MLO is exceeded, the conductor could sag excessively, come into contact with the ground or other objects, or even break. Therefore, it is crucial to carefully consider the MLO in all of these examples to ensure the safety and reliability of the structure or electrical system. In addition to the factors mentioned above, there are other considerations that can affect the MLO. Firstly, the presence of concentrated loads can reduce the MLO. A concentrated load is a load that is applied over a small area, such as a piece of heavy equipment placed on a balcony. Concentrated loads can create high stresses in the supporting structure, requiring a shorter MLO to prevent failure. Secondly, the presence of dynamic loads can also reduce the MLO. A dynamic load is a load that varies over time, such as wind gusts or seismic activity. Dynamic loads can create vibrations and oscillations in the structure, requiring a shorter MLO to prevent resonance and failure. Thirdly, the presence of corrosion or other forms of degradation can reduce the MLO. Corrosion can weaken the materials used in the structure, requiring a shorter MLO to maintain safety. Therefore, it is important to consider all of these factors when determining the MLO for a specific application. To ensure that the MLO is properly determined and maintained, it is essential to follow a systematic approach. Firstly, a thorough site assessment should be conducted to identify any potential hazards or constraints. This assessment should include a review of the soil conditions, the weather patterns, and the presence of any nearby structures or objects. Secondly, a detailed structural analysis should be performed to determine the appropriate MLO for the specific application. This analysis should consider all of the factors mentioned above, including the material properties, the load conditions, and the presence of any concentrated or dynamic loads. Thirdly, a comprehensive inspection program should be implemented to monitor the condition of the structure or electrical system over time. This program should include regular visual inspections, as well as more detailed inspections using specialized equipment such as ultrasonic testers or infrared cameras. Finally, any necessary repairs or maintenance should be performed promptly to address any issues that are identified. By following this systematic approach, it is possible to ensure that the MLO is properly determined and maintained, and that the structure or electrical system remains safe and reliable. In summary, maximum length of overhang, MLO, is a critical parameter in structural and electrical engineering. It represents the maximum distance an overhang element can extend beyond its support without compromising safety and stability. Understanding and adhering to MLO requirements is essential for preventing structural failures, ensuring the reliability of electrical systems, and protecting public safety. Whether designing a balcony, a canopy, or an overhead power line, careful consideration of MLO is paramount. In structural applications, MLO is influenced by material properties, load-bearing capacity, and support structure design, with engineers employing finite element analysis to determine safe limits. In electrical systems, MLO depends on conductor size, tension, weather conditions, and terrain, with specialized software and adherence to regulations like the National Electrical Safety Code guiding its implementation. Failure to comply with MLO can lead to severe consequences, including property damage, injuries, and power outages, underscoring the importance of meticulous planning, analysis, and maintenance. Other factors such as concentrated loads, dynamic loads, and corrosion can further impact MLO, necessitating a comprehensive approach to assessment and monitoring. A systematic process involving site assessment, structural analysis, inspection programs, and timely repairs ensures that MLO is properly managed, safeguarding the integrity and reliability of structures and electrical systems alike. Firstly, consider the implications of exceeding MLO in a bridge design. If the cantilevered sections of the bridge extending beyond the supporting piers exceed the calculated MLO, the bridge could experience excessive deflection, leading to cracking in the concrete or steel structure. This could compromise the load-bearing capacity of the bridge and potentially lead to catastrophic failure under heavy traffic loads. Secondly, in the context of building construction, imagine a large awning extending over a storefront. If the awning's MLO is not properly calculated and the supporting structure is inadequate, strong winds could exert excessive force on the awning, causing it to tear away from the building and potentially injure pedestrians below. Thirdly, consider the case of a communication tower with antennas mounted on extended arms. If the MLO of these arms is exceeded, the tower could become unstable, particularly under high wind conditions. This could lead to the tower collapsing, disrupting communication services and posing a significant safety hazard. Furthermore, in the design of aircraft wings, MLO plays a crucial role in determining the maximum allowable length of the wing extensions. Exceeding the MLO could lead to flutter, a dangerous aerodynamic phenomenon that can cause the wing to vibrate violently and potentially break off in flight. In the context of offshore oil platforms, the MLO of cantilevered decks and equipment supports must be carefully calculated to ensure the stability of the platform in harsh marine environments. Exceeding the MLO could lead to structural failure, causing equipment to fall into the sea and potentially leading to environmental damage and loss of life. Therefore, it is essential to recognize that MLO is not merely a theoretical concept but a critical parameter with real-world implications for safety and structural integrity. Proper calculation, design, and maintenance are essential to ensure that MLO requirements are met and that structures and electrical systems can perform safely and reliably throughout their service life.